In this tutorial, we're going to go through Laplace transforms and how to solve those symbolically in Python with Sympy. A Laplace transform transforms a function f of t from the time domain into the Laplace domain with this transform. And there are mathematicians who have come up with tables and have done this for many functions. And so you can just look up in the time domain, for example, and then convert that into the Laplace domain. So for example, a unit step might be 1 over s. And if you look at something like t, which is a ramp with slope 1, we just have 1 over s squared. Alright, so there are tables of those, or you can derive them yourself. Here is a derivation of just using a constant c, and that gives you this one right here, which is 1 over s, okay, or c over s if you have that constant out front. Alright, we're going to go through this in Python though and see if we can check some of our solutions. I often find it useful when I'm doing a derivation and just need to check it to use Sympy. And so we'll import Sympy, and I'll import it as SYM. Some people import it as SP, but that's often the same abbreviation for SciPy. Alright, and then from sympy.abc, I'm going to import some letters like S and T. Those are the ones that we need. I'll throw a couple of others in there like X, Y, Z as well. Alright, and then some other packages like Laplace transform. That's going to be a function that we're going to use to do the Laplace transform, and then inverse Laplace transform as well. Alright, and so let's do our first Laplace transform, going from t to s. Alright, so I'm going to have u be the result, and this is going to be Laplace transform of 5 times t. Alright, and that's this first one right here, which is going to be a slope in the numerator of 5 instead of 1. Alright, so let's see if that gives us the solution. Oh, I have not run this one yet. Okay, so let me run this one after I've imported the packages. Oh, I need to do comma t and comma s. So that tells me I'm going from the time domain to the s domain, and those are the variables that I use. Alright, and then what I want to do is just say u0, and then that gives me just the first one. If I just leave that out and say u, then it gives me the result, 0 and true. I just want to get that very first one though, which is 5 over s squared. Alright, let's do an inverse Laplace transform as well. Okay, I'm going to use inverse Laplace transform, and I'm going to convert u of 0, okay, that very first element, from s to t. So I'm just going to convert it back. Alright, and I see it's 5 times t, which we had before, and then this heaviside function. If it's just heaviside function of t, then you can just ignore it. It just basically means it's like a step function. It says it starts at time 0. Alright, let's go on to the next one. I'm going to have a function f, and here I'll just display it with that f down below. Okay, so here's a transfer function that relates an input to output. Let's say we want to do a partial fraction decomposition, because let's say, in a Laplace table, maybe we have this or that multiplied together, and we need to separate them into 2 individual parts. Okay, in some cases you see them multiplied together, others you need to separate. And so partial fraction decomposition is important. And so you can do that with Sympy as well. And that's going to be with the a part. Okay, so I need to break this one up into 2 individual pieces so I can find the solution with a Laplace table, or I can use Python as well. Okay, so there's partial fraction decomposition, and it computed an analytic solution to that. Alright, and then what we want to do now is look at the denominator of a transfer function. Okay, and this is going to be important for things like stability analysis or other things later, but we can do a lot of the algebra with Python. Okay, so here's just my polynomial that is in the root form, so I can easily see that one root is s equals 1, one is s equals 3, and then I have some others here. But I want to expand that. Okay, and so I'll expand d1 and have that result be d2. So this does a FOIL method. It calculates this polynomial. Let's also find the roots of that. We can find the roots of d2, and that will give us the value here, which is -1, and there's one of those roots. -3, there's also one of those roots. And then here's our next one, okay, with one root, and the final one with one root. So a total of 4 roots that it found symbolically. Let's go on to a little bit more complicated example now. This is a Python Sympy to compute symbolic solution to differential equations. Now we have this input, okay, where it's going to start at 1, have a step up, and then continue until time 3, and then ramp down to at time 5, and then be constant going over. All right. Okay, and then the transfer function is a stable system with 2 poles. Okay, those are the denominator roots, and 1, 0, which is a numerator root, which is s equals -1, and then 2, which is our s equals -3 in the denominator. So we want to figure out what the solution is. If this is our input, what is going to be the output given this transfer function? So we want to create the step and ramp signals as 3 individual functions, and we'll compute the system response to each of those 3 inputs and then add up the signals together. So let's go ahead and just break this one down. What we're going to do with that is combine it into basically 3 signals. All right, our first one is going to be a step up to 2 that happens at time 1. All right, and that's going to be step 2, right? Step to 2 at time equals 1. All right, our next one is going to be a ramp down that starts at time equals 3. So I'll go ahead and just do that in yellow here. So we're continuing until we hit time equals 3, and then it's going to have a -1 slope, and that will continue indefinitely. And then the third one that we have is going to start at time equals 5, and that will be a ramp up. What that will do is at this point it will cancel out any further decrease, and so that's how it levels out here at the very end. So we're going to add these 3 together, and those are going to be this is 2 divided by s. Okay, it was that step function that we saw. And then this next one, that is going to be -1 divided by s squared. Okay, and we're going to add some delay to these as well. And then this one is going to be +1 over s squared. All right, but this one starts at time equals 5. All right, time equals 5. So the way that we put that delay in there for each of these is we put in e to the minus s. Okay, so that's going to be -1 right here. Okay, or sorry, +1 right there. Okay, so -s, but that means it's going to be that amount of delay. All right, and let's do this over here as well. I'll do e to the -3s. All right, and then the final one, which is going to be e to the -5s. All right, that's going to be an amount of delay. Let's go ahead and put these 3 into Sympy and then compute the output response. All right, so we're going to import Sympy. I'll import my variables. I've already done that once, but I'll just do it again so it's all self-contained. I'll have NumPy in there as well. And then I'll have the inverse Laplace transform, matplotlib. All right, here are my inputs. Here's that first one. We have 2 over s e to the minus s. That's going to be a step up by 2 that starts at 1 second. And then I'm going to have this ramp down that starts at 3 seconds right here. And then I'll have the ramp completes at 5 seconds, so I've got to add that back in. All right, the next thing I'm going to do is create my transfer function. And that's going to be 5 times s plus 1 divided by s plus 3 squared. And then I'll calculate the responses to each. So y1 is going to be g times u1. I have y2 and y3. I'm going to compute each response individually and then add them up at the end. And then I'm going to do the inverse Laplace transform to get y1, y2, and y3 in the time domain. Okay, so I have, let me do that for u and y. I'm going to go from the s variable to a t variable. All right, I'll do that for u2 and u3 as well, just so I can see the solution. And then y2 and y3 as well. So there are all my inverse Laplace transforms to compute the solution, and I'll print y1. All right, let's generate some data for the plot. Now we have an analytic solution, but let's just generate this, and actually we can run this and then just see y1. It's going to run. You see the little asterisk. This one takes a little bit of time to get a symbolic solution, but it should print y1. All right, so there is my solution, and just this heaviside function means that you've delayed that. It's 0 before time equals 1, and then equal to 1 after that. All right, and then let's generate some data for the plot. I'll just do that with NumPy and linspace between 0 and 8, and let's put in 100 points instead of the default of 50. And then we'll put in some u values and y values as well. And then we'll substitute some numeric values for u and y, just so we can show it. Okay, so here we have a symbolic solution, but we want to plug in values for t. All right, for u, I'm going to look at all the range of times, and then I'm going to add, I started out with 0, so I'm going to add to that. And I'm going to substitute, so I'll do u dot subs, okay? So I'm going to cycle through each one of these individually, u1, u2, and u3 in this list. And then for each one, I'm going to substitute in the time, okay, the time that I computed right here, just to get a numeric solution. And then for y as well, I'll do that for all the times and substitute in the time. All right, and then I want to plot the results. I'll do that with matplotlib. And let me look at the US, YS, put a legend on there, and time, and then show it. So let's go ahead and calculate that again. You can see it takes just a little bit of time. When that turns into a number, then it will be done. And so there we go. We have our solution, and here is our output y. That is a summation of each of those 3 individual ones in that list. All right, well let's let's go on to a numeric solution as well. Now you can do this with ODE int in Sympy.integrate. There's a ODE integrator. You can look at this tutorial right here. There's also Python Gekko. So we're going to do this in Python Gekko instead. Okay, here's our transfer function in the Laplace domain, and we're just going to convert this back into the time domain. So anytime you see an s, it means it's going to be the derivative of y. Okay, and anytime you see like an s squared, that's the second derivative of y. And then with no s in there, it just means it's going to be equal to y. Okay, so we're going to convert it from the Laplace domain back into the time domain, and then solve that with a differential equation solver. All right, let's do this in Gekko. Now, if you don't have Gekko, let me just go ahead and insert a cell above. You can just do pip install Gekko. Okay, and if it's already there, then it will just show up as already satisfied. In this case, I've already installed it. Okay, so I'm going to have numpy matplotlib. I'll create the Gekko model, and I'll just say m is equal to the Gekko model name. If you say remote equals false, it doesn't use an internet connection. It solves locally. Time points for simulation, I'll say 81. And then I have, so just 0.1 seconds for each. If you put more, it'll calculate just a little bit slower, but you'll have maybe a little bit more accuracy as well. Alright, so let's go ahead and step up, ramp down, and then ramp complete. We'll just define this in the time domain instead of in the Laplace domain like we did before. Alright, so u between 11 to 31 is 2, and then I'm going to ramp down. So this is my ramp down on this. That is this total that we saw before. It's this total signal where it's going to come up and then down and then level out. Okay, so this is that ramp down right here, and then I'm going to have define my model. This is my u value, which is going to be equal to this u of t. So everything's in the time domain now instead of in the loss domain. And I'm going to have ud as well. That's going to be my derivative. Okay, and I needed that because I have the derivative of u right here. Alright, let me get rid of this just so I can see it, hopefully some of it at the same time. Okay, so there's the derivative of u, derivative of y, and then the second derivative of y. We'll need to do something with the second derivative as well. Calculate the derivative of y and then make it a second derivative. Okay, so there's an equation. I have u of d equals u. Okay, and then I have dy dt equals, in this case, y dot dt. And then dy dt equals plus, and then I have this as 6 plus 6 times y dt. So this is the first derivative of y. This is going to be the second derivative of y because I defined this variable as equal to the derivative of y. Alright, and then I'm going to do plus 9y and put the double equal sign there, and then I have the derivative of u. I had to do this because it has to be a variable in order to have the derivative associated with it. Okay, so here's my differential equation expressed in the time domain. And then we'll have a solver solve it. Okay, simulation options. I'll do sequential simulation mode with nodes equals 4. And then solve it. Tell it to not display the solver output. Okay, and I'll plot the results. I'll plot m dot time. Okay, those are the times that I requested. And then u dot value. And then I'll do y dot value as well. Alright, put a legend and time. And then let's just look at the speed of this one as opposed to the other one. So this one was fairly quick. Okay, if I click enter, I see a result fairly fast. The symbolic solution is a little bit slower. Alright, so numeric solutions are good if you have complex, like a nonlinear system that Laplace variables really won't work for. Also, if you have many differential equations, a couple differential equations where an analytic solution just isn't possible. And so use a numeric solution in that case versus an analytic or Laplace solution. But you get the same results that we did before. Alright, so let me just summarize what we've gone through so far with this. We started out with Laplace transforms and how to use Sympy by importing some of these variables and these Laplace transform and inverse Laplace transform functions. We showed 5 times t going to the Laplace domain and then back into the time domain. And then some other functions that are going to help us if we do need to use these Laplace tables like partial fraction decomposition or being able to factor or find roots and other things. And then we did this example solution where this was the input to our function and we wanted to calculate what is the output given this transfer function right here that relates inputs to outputs. And we did that with Sympy and showed the analytic solution right here, and then also created a plot by substituting in the time values. And then there's also the numeric solution that we did with Python Gekko, returning it to the differential equation form and then putting that into Gekko as a differential equation and then solving it. So this one gave us the same solution as the Sympy solution. I hope you enjoyed this. There's more information here in Laplace Transforms, including links. For example, if you wanted to run through this exercise and you wanted to use Google Colab, let's say you didn't have Python installed, you can just use this Google Colab link and click Run. And then for each of these, you can just do Control Enter, or you can run all, and you can see the same solutions that we came up with, but it's just running through a web browser instead of on your computer. So you can use Sympy even if you're on a platform where you can't install Python. You can still use it through a web browser and still be able to benefit from the Symbolic Python solutions. Okay, now if you're in Google Colab, you probably don't have, I'm going to run this one just to show it. And then if you do need to install Gekko here, just insert a code cell and again do pip install Gekko, and then it will install it locally for your session. Okay, and after that runs, then you can run the numeric solution as well. Okay, so there's your numeric solution with Gekko. Hope you enjoyed this tutorial. Feel free to leave comments or questions down below.